Hello everyone. Declaration 1. The copyright of this article or video belongs to the original author Da Wang. 2. The content of this article shall not be reproduced without the permission of the original author. Otherwise, it will be regarded as infringement. 3. Reprint or quote the content of this article. Please indicate the source and the original author. 4. For non-compliance with this statement or other illegal use of the content of this article, I reserve the right to pursue according to law. 5. The Chinese version of this paper has been uploaded to the internet, entitled 四色猜想的证明, which can be used as a reference for this paper. This article is separated in the 4 sections. Section 1, related concepts and properties of graph. 2, the one-way transferability of the road cycle model. 3, the invalidity of roadless cycle model. 4. The final proof of the four-color conjecture. Abstract. Coloring all spherical maps with only 4 colors, i.e., the four-color conjecture can be transformed into coloring of each single origin dot sufficient graph during a point splitting process. Taking this as a starting point, the author makes the following proof. First of all, according to the different treatment methods of the origin dot bridge structure in the origin-related cycle process, the origin-related cycle models are classified into 2 categories: rod cycle models and rodless cycle model. Secondly, it is proved that any single origin dot sufficient graph with only rod cycle models has a 4-color solute graph, and also the widespread non-existence of single origin dot sufficient graph with dotless cycle model is proved. Finally, it is proved that all spherical map have 4-color solute graph. Keywords: 4-color, origin-related process, rod cycle model, state bifurcation, rodless cycle model, time overlapping closed set. Introduction. The four-color conjecture was first proposed in 1952 by Francis Gauthey, a graduate of the University of London. The specific content is any spherical two-dimensional map can be colored by only 4 colors, and ensure that any 2 countries with a common border have different colors. Over the next 170 years, scholars around the world have tried numerous methods to prove the 4-color conjecture, including the following: 1. Computer exhaustion method. 2. Reduction to absurdity. 3. Spiral chain coloring. However, these methods or theories have the following defects. 1. Can't prove its applicability to the universe sense of spherical graphs. 2. Operability is not strong. Complex graphs can't be assigned in a relatively simple, intuitive, and efficient way. In this paper, the concepts of spiral rod structure and straight rod structure are proposed from the point of view of origin-related state cycle, taking single origin dot sufficient graph as the main analyzing object. The universal set of different single origin dot sufficient graphs is divided into two subsets by the condition of whether there is a spiral rod structure in any of the region-related in the origin-related cycle. 1. Straight rod graph set. 2. Spiral rod graph set. By the means of logical reasoning, it is proved that all graphs in the two graph sets have four-color slot graph, thus basically solved the above two defects. The following chapters will prove that any spherical map has a four-color slot graph. The general idea is as below. Map of all simply connected countries. 1. Define each country on the uncolored map as a color point. The lines between the dots represent the borders that exist between countries. Each country in Figure 1 corresponds to each color point in Figure 2, and the border between countries in the Figure 1 correspond to the lines in Figure 2. Figure 2 is the point graph of Figure 1. 2. According to the Theorem 17 of Chapter 4, the map has a four-color slot graph. Map with multiple connected countries. Each outward whole of each multi-connected country, together with the part of the country 1 as the edge of the whole, can be treated and processed as an independent map. In Figure 3, there are several independent gray empty regions containing other countries outside the country 1 color block, and each region can be regarded as an independent map together with the part of the country 1 as the edge of the region. According to Theorem 17 in Chapter 4, this independent map all have four-color slot graph, and then the whole map has four-color slot graph. Related concepts and properties of graph. 1.1. Sufficient graph and its related concepts and properties. Definition 1. G1 is a spherical graph which would be valued at its dots. If G1 has the following properties, the graph is a sufficient unique point connection graph, simply called sufficient graph. 1. Any 2 points of G1 that have a connection relationship, K1 and K2, have only one connection. 2. There are 3 boundary points of the minimum region, defined as the minimum region, surrounded by points and lines in G1. Figure 2 is a sufficient graph. The minimum region S1, surrounded by 5 to 4 points and lines between any 2 points of these 3 points, is a minimum region. In Figure 4 and Figure 5, the former has more than one line at 1 and 3 points. In the later one, the smallest region, S1, enclosed by 1, 2, 3, and 4, has 4 boundary points, so any one of them is not a sufficient graph. Definition 2. For spherical graph, if each point of G1 is assigned one of the 4 values of A, B, C, and D, when all points of G1 is assigned, the resulting graph G2 is called an assigned graph of G1. If any 2 points K1 and K2 with a line in G2 are assigned differently, then G1 is an assignable graph. G2 is called 4-color solute graph of G1. Definition 3. The 4 color values A, B, C, D in graph G1 used for coloring. If 2 of the values are determined, then the remaining 2 are dual values of A and B. Definition 4. There is a sufficient graph G1, and if spherical graph G0 has the following properties, then G1 is a same-point sufficient graph of G0. 1. There is one-to-one correspondence between the points of G1 and G0. 2. If there is a line between K1 and K2 in G0, then there is also a line between the corresponding points K1 apostrophe and K2 apostrophe in G1. Theorem 1. Let G1 be the same point sufficient graph of G0. Then if G1 is an assignable graph, G1 is assignable, then G0 is also assignable. That is, G1 is assignable is a sufficient condition for G0 is assignable. Proof. Let G1-1 be a 4-color solute graph of G1. Now, the value of all points G1-1 is copied to the corresponding point of G0 to get the graph G0-1. If G0 is not assignable, then G0-1 has 2 points, P1 and P2, and the same value, with the same value. According to the definition of sufficient graph, the connection relation F1 of P1 and P2 also exists in G1, and F1 is also present in G1-1. That is, P1 and P2 of G1-1 are also adjacent and of the same value. This contradicts the condition that G1-1 is a 4-color graph. Therefore, G0-1 is a 4-color solute graph. That is, G0 can be assigned. QED. 1.2. Related concepts and properties of origin dot and a single chain. Definition 5. Any dot which is divided into 2 adjacent points on the map is called the origin dot, OD. In figure 6, the alpha dyed dot is divided into 2 adjacent points, alpha 1 and alpha 2. In figure 7, the alpha 1 dash alpha 2 dot pair is OD. An assigned graph G1 with one and only one OD is called a single origin dot graph, single OD graph. Definition 6. A point bit 1 connected simultaneously with the constituent points of 2 connected points alpha 1 dash alpha 2 in a sufficient graph and located at the boundary of the same minimum region as alpha 1 and alpha 2 is called a bridge point of alpha 1 dash alpha 2. In figure 6 and figure 7, bit 1 and bit 2 are the bridge points of alpha 1 dash alpha 2. The bridge point of the OD is called the origin bridge point. Theorem 3. In a sufficient graph G1 consisting of points greater than 3, there are and only 2 bridge points for any connecting point pairs, alpha 1 dash alpha 2. Proof. Since the constituent points of G1 are greater than 3, the number of minimum region of G1 is at least 3. According to the definition of sufficient graph, any line, such as the line from alpha 1 dash alpha 2, is the common boundary of only the two smallest regions, S1 and S2. After removing alpha 1 dash alpha 2 from the boundary points of S1 and S2, only one point remains. Let's say S1 is left with beta 1, S1 is left with beta 2. Since the constituent point of G1 is greater than 3, beta 1 and beta 2 are different. According to the definition of bridge point, beta 1 and beta 2 are the bridge points of alpha 1 dash alpha 2. So theorem 3 is true, QED. Definition 8. Two bridge points beta 1, beta 2 of the same connected point pair dash 1 alpha 1 dash alpha 2 are called bridge points pair of alpha 1 dash alpha 2. The bridge points pair of OD is called origin bridge points pair. Definition 9. The graph G2 obtained by assigning each point of graph G1 is one of 4 values, such as A, B, C, D, is called a graph state of G1. Definition 10. In the sufficient assigned graph G1, there is a set S1. S1 is a single chain or single ring of G1 if the following conditions are met. 1. There is a sequence or loop sequence XL1 consisting of all points in S1. 2. XL1 has no duplicate items. 3. For any point in XL1, such as Km, its neighbors in XL1 are set to Km minus 1, Km plus 1 in G1. The connection relationship between Km and the other points in XL1 is as follows. A. Km is connected to both Km minus 1 and Km plus 1. Km add 1. B. Km is not connected to any point in XL1 which is not of Km minus 1 or Km add 1. Definition 11. In an assigned graph G1, if there is a single chain L1 which consists of points of only 2 colors, L is called a general 2-color chain. If L1 is a single ring structure, then L1 is called a general 2-color chain ring. Definition 12. There is a single ring in the assigned graph. G1 has 2 subsets, S1 and S2. The following conditions exist. 1. Points in S1 consist of all points of G1 on one side of L1. The points in S2 consist of all points of G1 on the other side of L1. 2. S1 is the set of all points in S1 and the connection relationship between these points in G1. S2 is the set of all points in S2 and the connection relationships between these points in G1. S1 or S2 is called the ring region of L1 in G1. If there are 2 points K1, K2, K1 belongs to S1 and K2 belongs to S2, then K1 and K2 are said to be separated by L1. Definition 13. There is a point set S1 in the assigned graph G1. Do the following for all points in point set S1. 1. If the value of K1 is A, change its value to B. If the value of K1 is B, change its value to A. If K1 has a value of C or D, do not change. The above operations are called value swaps for S1. Definition 14. As shown in Figure 8, in the assigned graph G1, there is a bridge point pair bit 1, bit 2 of connected point pair alpha 1 dash alpha 2. There is a 2-color chain L1 who does not contain points of the same value as alpha 1 and alpha 2. If L1 connects bit 1 to bit 2, so the L1 is a bridge chain of alpha 1 dash alpha 2. The bridge chain of OD is called the origin bridge chain. Theorem 4. A single origin graph G1 can be transformed into a 4-color graph if there is an origin bridge chain. Proof. As shown in Figure 8, when the original bridge chain exists, L1 may be set as the BC chain, and the single ring composed of L1 and alpha 1 is set as L1 apostrophe. Do $D. So we can see do A change D on the alpha 2 side of L1 apostrophe. And since the value of alpha 2 changes to D, alpha 1 is with different value from alpha 2, so the theorem holds, QED. Definition 15. In the single OD graph G1, the 2-color ring L passing through the 2 points of the OD is called the bridge resistance of alpha 1 dash alpha 2. In Figure 9, the AD 2-color ring L1 and the AD 2-color ring L2 are the bridge resistance of bit 1, bit 2, and the OD. Theorem 5a. In sufficient graph G1, points alpha 1 and alpha 2 are separated by the 2-color ring L1. If there is a 2-color chain L2 connecting alpha 1 and alpha 2, then L2 must have a common point K with L1. Proof. As shown in Figure 10, according to the definition of connected region and the 2-color ring, if this theorem is not true, then the 2-color ring L1 does not exist. So the theorem holds, QED. Definition 16. There is a subset S1 in the assigned graph G1. If S1 meets the following conditions, then S1 is a 2-color chain graph of G1 with respect to AD value. 1. All points of S1 are the ones in G1 whose value are A or B. 2. All connections relationships in S1 are the connection relationships all points in S1 in G1. As shown in figure 55 of Appendix 1, the graph formed by all AD points and blue line segments is a two-color chain graph of figure 15 with respect to AD values. Definition 17a. If to any 2 points k1 and k2 in region G1, there exists a single chain L1 with k1 and k2 as the first and the last points, then G1 is called a continuous structure. Theorem 5. Sufficient graph G1 is a 4-color solute graph. If G1 has the following conditions, the following conclusions are valid. Condition 1. 1. The assignment of the points of G1 is selected in the set ABCD. 2. There is a two-color ring L1, and the value of the points of L1 are A or B. 3. There are 2 points alpha 1 and alpha 2. Alpha 1 and alpha 2 are separated by L1. Conclusion 1. There is no chain L2 with the following properties. A. L2 connects alpha 1 to alpha 2. B. The values of the points of L2 are C or D. Conversely, if G1 has the following conditions, the following conclusions are valid. Condition 2. 1. There are 2 points, alpha 1 and alpha 2. 2. There is no chain L2 with the following properties. A. L2 connects alpha 1 to alpha 2. B. The values of the points of L2 are C or D. Conclusion 2. There is a two-color ring L1 satisfying the following conditions. A. The values of the points of L1 are A or B. B. Alpha 1 and alpha 2 are separated by L1. Proof. Figure 11 satisfies condition 1. From theorem 5a, L2 must intersect L1 if it connects alpha 1 with alpha 2. Let's see that one of the points of the intersection exists is K. Since K is on L1, the value of K is either A or B and can't be either C or D. This contradicts the condition that point K is also on L2, so conclusion 1 holds. Under condition 2, there are the following situations. 1. The value of both alpha 1 and alpha 2 are C or D. From condition 2, there are two CD two-color chain graph, GCD1, GCD2, with the following properties. A. GCD1 is the largest CD two-color chain graph containing alpha 1 in G1 as a continuous structure. Condition 3. B. GCD2 is the largest CD two-color chain graph containing alpha 2 in G1 as a continuous structure. Condition 4. C. No point in GCD1 is connected to any point in GCD2. Otherwise, there is a CD chain L2 that connects alpha 1 to alpha 2 which contradicts with condition 2. Condition 2. As shown in figure 12, according to the definition of sufficient graph, there exists a multi-connected graph S12 with respect to GCD1 and GCD2. In S12, there exists a ring L1, and L1 has the following properties. A. L1 separates GCD1 and GCD2 in the following GCD2 in the two different ring regions. S21, S22 of L1, condition 5. B. L1 is the ring closest to GCD1, condition 6. As shown in figure 13, if point K1 exists in L1 and K1 is not connected to a point K0 in GCD1, then according to the definition of sufficient graph, in the ring region S21 of L1 containing GCD1, there is a chain L1 apostrophe in S12 connecting to the adjacent point gamma 1, gamma 2 of K1 in L1. That's the chain from gamma 1 to gamma 2 in L1 that does not pass through K21 be L1 2 apostrophe. The ring L3 consisting of L1 apostrophe and L1 2 apostrophe lies entirely with S12, and L3 separates GCD1 and GCD2 in the two different ring regions of L3. Since L3 is closer to GCD1 than L1, which contradicts condition 6. All points in L1 are connected to points in GCD1. According to condition 3 and the definition of sufficient graph, if L1 has a point with value C or D, GCD1 is not the largest CD two-color chain graph containing alpha 1 in G1 as a continuous structure, which contradicts condition 3. So L1 is a ring whose points value are A or B. According to condition 3, GCD1 includes alpha 1. By condition 4, GCD2 includes alpha 2. According to condition 5, conclusion 2 is true. 2. One of the points of alpha 1 and alpha 2 is with the value of A or B, and the other is with the value of C or D. Let's say alpha 1 is with the value of A. Since G1 is a sufficient graph and a 4-color absolute graph, there is a point K1, which is connected to alpha 1 and with the value C or D. According to the condition 2, there is no CD chain connecting K1 and alpha 2. So by case 1, there is an AB ring separating K1 from alpha 2. Now, the relative position of alpha 1 and L3 exists in the following two cases. A. Alpha 1 is not in L3, then alpha 1 and alpha 2 are separated by L3, and the conclusion 2 holds. B. Alpha 1 is on L3, as shown in figure 14. In the ring region S31 of L3, there is a point K2 connecting to alpha 1, and the value of K2 is C or D. By condition 2, there is no CD chain connecting K2 and alpha 2. So by case 1, there is an AB ring separating K2 from alpha 2. According to condition 7, if conclusion 2 is not true, then L4 satisfies the following properties. 1. Alpha 1 is in L4. 2. All AB rings that can be formed by the points of L3 and L4 can't separate alpha 1 from alpha 2. According to the condition 8, the following conclusions exist. A. There is an adjacent point bit 3 of alpha 1 in L4. B. Let the two adjacent points of alpha 1 in L3 be gamma 1, gamma 2, gamma 3 is different from gamma 1 and gamma 2. According to condition 9 and the definition of four-color solute graph and the definition of sufficient graph, there is a point K3 in one side A, of gamma 3 dash alpha 1 dash gamma 2 in figure 15, and neither K1 or K2 are inside A. K3 has the following properties. A. The value of K3 is C or D. B. K3 connects to alpha 1. C. K3 and alpha 2 are located in the same ring region as 3,1 of L3. K3 and alpha 2 are located in the same ring region as 4,1 of L4. According to case 1, there is an AB ring separating K3 from alpha 2, and so on. By being done in the same manner to the subsequence, there will be an infinite number of different points with the value of C or D connected to alpha 1. This contradicts the condition that there are finite points in G1. So conclusion 2 is valid. 3. Both alpha 1 and alpha 2 are with the values of A or B. Since G1 is a sufficient graph, and a four-color solute graph then there is a point K11 which connects to alpha 1, and the value of K11 is either C or D. There is a point K21 which connects to alpha 2 and with the value of and is with the value of C or D. It is known from 2 that there is an AB ring L3 that separates alpha 1 from K21. Now, the relative positions of alpha 2 and L3 exist in the following two situations. A. Alpha 2 is not in L3, then alpha 1 and alpha 2 are separated by L3, and the conclusion 2 holds. B. Alpha 2 is in L3. As shown in figure 16, there exists a point K22 located in the ring region as 3,1 in L3. K21 is not in as 3,1, and the value of K22 is C or D, and K22 connects to alpha 2. It is known from 2 that there is an AB ring separating alpha 1 from K22, as shown in figure 17. According to the condition 10, if conclusion 2 is not true, then L4 should satisfy the following properties. 1. L4 passes alpha 2. 2. all AB rings that can be formed by the points of L3 and L4 can't separate alpha 1 from alpha 2. According to condition 11, the following conclusions exist. 1. There is an adjacent point gamma 3 of alpha 2 in L4. B. Let the two adjacent points of alpha 2 in L3 be gamma 1, gamma 2. Gamma 3 is different from gamma 1 and gamma 2. According to condition 12, and the definition of four-color solute graph and the definition of sufficient graph, there is a point K23 in one side A, of gamma 3 dash alpha 1 dash gamma 2 in figure 17, and neither K21 or K22 are inside A. K23 has the following properties. A. The value of K23 is C or D. B. K23 connects to alpha 2. 3. K23 and alpha 1 are located in the same ring region as 3,1 of L3. K23 and alpha 1 are located in the same ring region as 4,1 of L4. According with case 2, there is an AB ring L5 separating K23 from alpha 1, and so on. By being done in the same manner to the subsequence, there will be an infinite number of different points with the value of C or D connected to alpha 2. This contradicts the condition that there are finite points in G1, so conclusion 2 are valid. Therefore, if conclusion 2 is true, condition 2 is true, conclusion 2 is true. To sum up, theorem 5 holds QED. 1.3 Related concepts and properties of OD rings. Definition 17. G1 is a signed graph. If there are two connected points K1, K2 in G1, and K1 and K2 have the same value, K1, K2 is called same value connected points point pair, referred to as the same value point pair. As a signed graph, G1 with only one same value point pair is called a single OD assigned graph. Single OD graph for short. Definition 18. There is a point K1 in the two-color chain graph G1, and if the number of points connected to K1 in G1 is less than 2, then K1 is called the endpoint of G1. Otherwise, K1 is called a non-endpoint of G1. Definition 19. JG1 is a two-color chain graph with the following characteristics. 1. JG1 has two endpoints K1 and Kn. 2. JG1 is a continuous structure. 3. K1 is connected to K2 in JG1, and K1, K2 is the only same value point pair in JG1. Applying A change B to the values of all points of JG1 except K1, Kn is called same value point pair transfer from K1 to Kn in JG1. JG1 is called same value point pair transfer graph of K1 dash to dash Kn path. Definition 20. G1 is the AB two-color chain graph or sufficient graph G0. K1-K2 is the unique same-value point pair of G0. G1 is a subset of G1. G1 satisfying the following conditions is an origin transform structure of G0 from K1 to Kn. 1. G1 is the same value point transfer graph from K1 to Kn. 2. G1 is a continuous structure. 3. K1 and K2 exist in G1. 4. In G1, the maximum continuous structure where G1 locates is G11, and the subset G12 of G11 after removing G1 is still a continuous structure. 5. G1 is only connected to G12 at the point of K1 and Kn. Definition 21. If G1 is an origin transform structure of G2 from K1 to Kn, the same value point pair transfer from K1 to Kn is G1 is called the OD change process of G0 with respect to G1, also called the origin change of G0 with respect to G1. Origin changing process is also called OD transfer process. Theorem 16. If the sufficient graph G0 is a single OD assigned graph, the graph G1 obtained by OD transfer process is still a single OD assigned graph. Proof. As shown in figure 18 and figure 19, the latter is a graph obtained by OD transfer process from the former. By definition 20, G1 consisting of AB value points is the origin change structure of G0 from K1 to Kn. After the original change of G1, the value of K1 Kn is unchanged, and the value of K1's adjacent point K2 is different from K1. The adjacent point Kn minus 1 of Kn has the same value as Kn, so G1 only contains a pair of adjacent points with the same value Kn minus 1 dash Kn. Let the point of the G12 structure connected to K1 be K0, and the point of the G12 structure connected to Kn be Kn add 1. Since the value of K1 and Kn do not change, K1 and K0 have different values, and Kn and Kn add 1 have different values. Therefore, there is no same value point pair combined with both point in G1 and point in G12. In addition, the other pairs of G0 after the removal of G11, the remaining set G0 apostrophe of G0 do not contain points with A and B value as the adjacent point to G1. There's no same value connected point pair combined with both point in G1 and point in G0 apostrophe. Together with the fact that there are no same value connected point pair in the union set of G12 and G0 apostrophe, G2 obtained after the OD transfer process of G1 in G0 is still a single OD graph QED. Theorem 7. In sufficient graph G1, if point K1 is connected to point K2 and the chain ring LS passes through the K1-K2 point pair, that is through K1, K2 and the line between them, but not through any of the bridge points of the K1-K2 point pair, bit 11, bit 12, then bit 11 and bit 12 will be separated in two different ring regions of LS. Proof. Since the connections of K1 and K2 are part of LS, the minimum region S1 surrounded by K1, K2, bit 11, and the minimum region S2 surrounded by K1, K2, bit 12 are located in two different ring regions, LS-1 and LS-2 of LS. May wish to assume that S1 is located in LS-1, S2 is located in LS-2. Then bit 11 is either located inside LS-1 or located on LS. By the premise that LS does not pass bit 11 or bit 12, excluding the later, so bit 11 is located inside LS-1. Similarly, bit 12 is located inside LS-2 QED. Theorem 8. Two-color chain graph G1 is a continuous structure. G1 has a subset G11. G12 is the complementary set of G11 with respect to G1. If a single ring L1 exists and the following conditions are true, then the following conclusion is true. Condition 1. All L1 is in G1. 2. G11 contains at least 2 points K1, K2 of L1. 3. G12 contains at least 1 point K0 of L1. Conclusions 1. G11 contains at least 2 different points K3, K4. 2. K3, K4 is located on L1. 3. K3, K4 are connected to points on G12. Proof. According to the definition of single ring, there are two single chains, L11, L12, on L1 that satisfy the following conditions. 1. L11 connects K1 to K0. 2. L12 connects K2 to K0. 3. L11 and L12 have no common points. Since the points that make up L11 and L12 all come from the two sets of G11 and G12. 1. There is a point K3 on L11 belonging to G11, and K3 is connected to the point on G12. 2. There is a point K4 on L12 belonging to G11, and K4 is connected to the point on G12. 3. K3 and K4 are not the same point. Otherwise, L11 and L12 have a common point, which contradicts condition 3 above. Therefore, the theorem holds QED. Theorem 9. In the single OD sufficient graph G1, there is a region transform structure DG1 from K1 to Kn. The adjacent point of K1 in JG1 is K2, and the adjacent point of Kn is Kn-1. The bridge points for K1-K2 are bit 11 and bit 12. The bridge points for Kn-1-Kn are bit beta21 and beta22. JJ1 has the following properties. 1. J1 has two-color single chain composed of the dual color of JJ1. 2. L1 and L2 have no common points. 3. One endpoint P11 of L1 is the bridge point to K11, and the other endpoint P12 of L1 is the bridge point to Kn minus 1 dash Kn. 4. One endpoint P21 of L2 is the bridge point beta12 of JJ1's front OD, and the other endpoint P22 of L2 is the bridge point beta22 of JJ1's rear OD. Proof. Suppose that the structure is in definition 20 still exists in this proof. At the same time, JJ1 is set as the origin transform structure of the AD two-color chain graph. Then the following conclusion is true. 1. K1, K2, Kn minus 1, Kn are located on the same AD ring Ls in J1. 2. There is no AD ring Lk separating K1 from Kn. 3. The four bridge points beta11, beta12, beta21, beta22 of the front and the rear OD of JJ1 meet the following properties. A. Any point of beta11, beta12 is connected to at least one point of beta21, beta22 by CD chain. B. Any point of beta21, beta22 is connected to at least one point of beta11, beta12 by CD chain. Proof 1. There is an AD single chain LS1 in J12 connecting K0, K1's adjacent point in J12, and Kn at 1, Kn's adjacent point in J12. Therefore, it is only necessary to prove that there is an AB single chain LS1 which is in JJ1 connecting K2 and Kn minus 2, and also LS1 does not pass through either K1 or Kn. Assuming that no such LS2 exists, any AD single chain LS2 apostrophe that connects K2 to Kn minus 1 entirely within JJ1 must pass a point in either K1 or Kn, as shown in figure 20. Let's see this point is K1. Since K1 is the endpoint of JJ1 and is not the boundary point of KS2 apostrophe, there is a point K0 apostrophe which is one of K1's two adjacent points in LS2 apostrophe, and meanwhile K0 apostrophe is in G12. This contradicts the condition that LS2 apostrophe is located in JJ1. Similarly, LS2 can not pass Kn, so 1 is true. Proof of 2. As shown in figure 21, assuming the presence of Lk, K1 and Kn are located in two different regions separated by Lk. Since there is an AB chain LP connection between K1 and Kn in JJ1, by theorem 5a, there is a point phi 2 of Lk located in JD1. Similarly, there is also a point of Lk phi 1 located in G12. Since points of Lk exist only in JD1 or G12 by the definition of ring, there must be a point gamma 1 in Lk, which lies in JD1, and gamma 1's adjacent point gamma 2 lies in J12. Since Lk separates K1 and Kn, gamma 1 is different from K1 or Kn. Therefore, JD1 has at least 3 points K1, Kn, gamma 1 connecting to J12. This is in contradiction with the fact that the region transform structure, JD1 has only 2 points K1 and Kn connecting with J12, so 2 is true. Proof of 3. Assuming that 3 conclusion is not valid, then there is an AB ring L beta, which separates a point of beta 11 or beta 12 from the 2 points of beta 21 and beta 22, or a point of beta 21 or beta 22 from the 2 points of beta 11 and beta 12, may wish to set L bit to separate beta 11 from beta 21 and beta 22. If L bit does not pass through K1 or Kn, then K1 and Kn are separated by L bit by applying topology relation, which contradicts 2. So L beta pass through K1 or Kn. Let L beta pass through K1. There are the following subcases. A. L beta does not pass Kn point. 1. L beta passes K2, as shown in figure 22. Since K1 is the endpoint of JD1, K0, which is the adjacent point of K1 on L bit rather than K2, is not in JD1. So K0 is in J12. Since the points in L bit are either in JD1 or J12, and L beta has more than 1 point in JD1, K1, K2. By the definition of single ring, JD1 has at least 2 adjacent points of L beta with J12. Let the 2 points be K1 and Kp. Since Kn is not in L beta, Kp is not Kn. Therefore, there are 3 points K1, Kn, Kp adjacent to J12 in JD1, which contradicts the condition that there are only 2 points adjacent to J12 in JD1. Therefore, this situation does not exist. Two, L bit does not pass K2, as shown in figure 23. Since bit 11 connects with K2, bit 11 and K2 are located on the same side of L beta. By the condition, bit 21 and Kn are located on the other side of L beta. That is, K2 and Kn are separated by L beta. Then, the AB chain LP from K2 to Kn in JD1 has an intersection point phi 1 with L beta. Therefore, there are at least 2 points of L beta in JD1, K1, phi 1. In addition, since K1 is the endpoint of JD1, and the adjacent point of K1, gamma 1, gamma 2 in L beta are all located in J12. By the definition of single ring, J1 has at least two adjacent points of J12 in L beta. Let them be K1 and phi 2, respectively. Since Kn is not in L beta, phi 2 is not Kn. Therefore, there are 3 points K1, Kn, phi 2 adjacent to J12 in J1, which contradicts the condition that there are only 2 points adjacent to J12 in J1. That is, the situation does not exist. B. L beta passes Kn 1. L beta passes K2. Since L beta does not pass Kn minus 2, n minus 1, otherwise beta 21 or beta 22 will be on the same side of L beta as beta 11, which contradicts known conditions. And Kn is the endpoint of J1, and the two adjacent points of Kn in L beta, gamma 1, gamma 2, are in J12. As shown in figure 25, according to the definition of single ring, there is a single AD chain, L beta 1, from gamma 1 or gamma 2 to K2, which does not pass through point K1 or Kn. According to the definition of single chain, there is a point phi different to K1 or Kn in L beta 1, which is located in J1 and is adjacent to J12. It contradicts the condition that there are only 2 points adjacent to J12 in J1. That is, the situation does not exist. Two, L beta does not pass K2. As shown in figure 26, L beta does not pass Kn minus 1 known by 1. Since beta 11 and beta 21 are separated by L beta, and beta 11 is connected to K2, and beta 21 is connected to Kn minus 1, K2 and Kn minus 1 are separated by L beta. Therefore, the AB single chain, the AB single string chain, the AB single chain LP located in J1, which connect K2 to Kn minus 1, has an intersection point phi 1 with L beta. Since K1 is the endpoint of J1, the 2 points gamma 1, gamma 2 adjacent to K1 in L beta are located in J12. Similarly, the 2 points gamma 3, gamma 4 adjacent to Kn in L beta are also located in J12. According to the definition of single ring, there is a single AB chain L beta that starts from phi 1 to one of the points of gamma 1, gamma 2, gamma 3, and gamma 4 that does not pass through either K1 or Kn minus 1. There is a point phi 2 in L beta 1. Phi 2 is the connection point with J12 in J1, and phi 2 is different from K1 and Kn. It contradicts the condition that there are only 2 points adjacent to J12 in J1. That is, the situation does not exist. Above all, when L beta passes through K1, all the situations do not exist. So L beta does not pass through K1. Similarly, it can be proven that L bit does not pass through Kn. Therefore, there is no AB chain L bit separating bit 11 from bit 21 and bit 22. That is, bit 11 is connected to at least one point of bit 21 and bit 22 by CD chain. In the same way, it can be proven that bit 12 is connected to at least one point of bit 21 and bit 22 by CD chain. In the same way, it can be proven that any point of bit 21 or bit 22 is connected to at least one point of bit 11 and bit 12 by CD chain. So 3 is true. In the combination with the property of 1 and 3, as shown in figure 27, there must be a CD chain L1 or L2 of 3 in each ring region, S1 or S2 of LS of 1. It can be assumed that L1 is from bit 11 to bit 21 in S1, and L2 is from bit 12 to bit 22 in S2, and L1 and L2 have no common points. Otherwise, S1 and S2 have intersection, which contradicts the definition of ring region of a single ring. That is, the theorem holds QED.